Proceed with the program. We will hear Professor Jurica Dujakovic. Slađana will share his presentation with us. Jurica, please.
Good morning, or whatever it is now. It's still morning. I will talk about microalgae production systems. So before we start with the different systems, let's try to figure out what we basically need to know and what kind of basic components we need in order to design the system. So the first thing we have to know is the biology of the species we want to grow, biology of the aquatic organisms we want to grow. And
Jurica, sorry, I'm interrupting you. You didn't share your screen. You don't see your screen on the virtual session. Perfect, thank you.
okay now? All right.
Yes, it's fine.
So we work with aquatic organisms, we need water. And in order to hold water, we need some kind of enclosure. So basically we need tank, or we need pond, or we need cylinder, we need something where we're gonna hold this water. Then we need water, preferably sterile water with nutrients, vitamins, minerals, everything what is needed for the species of algae to grow. Then we need a source of energy. It's usually the sun and the source of carbon. Because our algae, if we don't move the water, if we don't create some kind of vertical or horizontal moving of the water, will settle on the bottom. So we need some kind of device that will hold this water in that suspension, hold this algae into suspension, and allow every organism to frequently be exposed to light. So if we start with a very basic system and we try to mimic nature, and we dig a pond and fill the pond with the water, with the sterile water, with nutrients and minerals and everything, what is needed for the optimal growth for the algae. We inoculate that. And we include some kind of mixing device. We can include bubbles, propellers, or something like that. We're gonna get a simple production system for our algae. So, and on the other side, if we wanna build something very sophisticated, we can build some completely enclosed cylinder, completely enclosed enclosure of some shape. We can sterilize it, fill up with the sterilized water, of course, put all the relevant nutrients, vitamins, and minerals, somehow put mixing device, and then try to control every relevant parameters for growth. So on the other side, we have something what so we have something what we call open system, what would be our pond, and then closed system, what would be this cylinder where we completely control the situation, completely control all the environmental parameters relevant for the growth and of course for the survival of the organism we want to grow. In between, we have lots of hybrid systems we will talk about. So if we have open system, we talk about ponds, tanks, raceways, or something like that. And closed system, we call this different kind of bioreactors. So we have advantages and disadvantages of this simple system and of this sophisticated system. Of course, the advantages of open system are low investment and easy to scale it up, and basically easy management. It's more difficult to control the sophisticated closed systems, and production is usually lower because we are talking about smaller enclosures than when we talk about ponds that can be couple of hectares. Closed system is safer, and you can really control the situation in the enclosure you have, but the capital costs are usually very high. If we talk about algae, we can create 3 different conditions: photoautotrophic conditions, when we need light; heterotrophic conditions, when we need, we'll see, a different source of carbon and energy; and then mixotrophic, because some algae like the situation when you grow them under light conditions in the open system, but you can add a little bit, I don't know, what a little bit of yeast, let's say, and they're going to grow faster. So if we talk about closed system, then we talk about 2 different reactors: photobioreactor and fermenters or fermenters. I don't know, we have here native English speakers. I don't know what is really correct, fermentor or fermenter, because I have found both in the literature. So I used fermenter here. So photobioreactors is, bioreactor is, closed vessels, usually cylinder or cone or something like that, where the energy is supplied via electric lights, usually. Fermenters are closed for heterotrophic production, and usually we supply energy as organic carbon. Mostly photobioreactors are mostly used because most of the algae are more phototrophs than heterotrophs. So, and there is a multitude of photobioreactors. I wouldn't say on the market, there are not a lot of them on the market, because most of them are custom made. So if you go to different facilities, you will see very different kind of photobioreactors. So you have tubular, cylindrical, conical, flat side vessels, and of course you will see wide variety of light sources. So if we want to build a bioreactor, if we want a photobioreactor, if we want to design it, then first we have to decide how to provide light. What is our source of light? Then how to circulate the algae, how to mix the whole media, growing media we have in the enclosure. Then which material we're going to use to build the cylinder or cone or whatever shape this enclosure is. Then how to provide and how to remove the CO2, or how to remove oxygen. And then of course how to control some other relevant parameters like temperature and pH. And as I say, they're usually customized, and it's a very limited availability on the market. Building material, you can use glass, acrylic, and they say that UV stabilized acrylic is superior because it's lighter, more flexible, stronger. It's easier to bond. It's easier to use that, and cheaper than some kind of inox or some kind of different material. You don't have to be an engineer to construct photobioreactor, so it doesn't require some engineering skills to build it. So it's, and if you want to control the system, if you want to control some relevant parameters in it, you can use controlling system off the shelf, especially pH control, temperature control, that is easy available, and you can include this in the design. So we can talk about a cylinder, build of acrylic, build of stainless steel, the source of light. So light and water never really come into contact. So you can have another glass cylinder when you could put the lights, when you can put the lights outside. So it's a different kind of system you can use. And of course, depending of which species of algae you grow, you can supply the light continuously, or you can design the whole system so you can have dark and light cycles. Of course, the name is photobioreactor, so light is one of the most important parameters. Of course, when light penetrates through the medium and it gets reflected, it gets refracted, and you have to be careful, and you have to put this into consideration. How thick is the media from the light to the end of your cylinder, and then how to design the inside of bioreactor to minimize reflection, and it's usually the best thing if you build it from the flat. If you have a flat surface, then if you have curved surface when light reflects in the different angles. And of course, chlorophyll absorbs the lights very intensively, so you have to be very careful. So your device supposed to be a very thin, or you have to include some mixing component in order for every cell or every organism gets to the light exposure frequently. So the sources of lights are, light lamps can be incandescent. They are inferior to the lamps that are seldom used now. So you're going to use fluorescent or high intensity discharge lamp to supply the light. So these are examples of bioreactors. So you can see the light is in the middle in some kind of glass cylinder here, and you have the lights here where we have this photobioreactor with the flat surface and with two different rows of light inside. So you have a little thin let's say inside tank filled with water and algae, so light can very easily penetrate through this. This is the different story. You have something like tube and another tube in it, and in the second tube you have light, so light can be dispersed evenly around the tube. This is something similar. The cylinders with the light and with the air bubble to assure the vertical circulation, so you can have a constant moving of light and constant moving of the population of microalgae. This is one photobioreactor, flat-sided again, with fluorescent lamp for mass production of algae. This is, I think, the University of Arizona. And now I want to show you it was a shellfish hatchery where we use plastic bags with the air, so oxygen, CO2 supply, and we design our own bioreactor. You can see it here in the. You can see it here. It was a plastic cylinder with the 6 fluorescent lamp. Each lamp was in the glass cylinder, and this is not in use yet, so we were supplying that with the media, and take out 1/3 every week. So we were established some kind of continuous culture in this photobioreactor. So we need this. Of course, we need optimum light. We need adequate gas exchange, and we need temperature control and pH control. So we can use usually in the photobioreactor, we mix the culture with the airlift or just with the bubbled CO2, air CO2 mixture. So we use air pumps, and we can inject a little bit of CO2 in the air stream. So why introduce CO2 if we have only 0.33% of CO2 in the air bubbles? It will limit the growth. So we add more. It's good to add more CO2. So between 0.2 and 5% in the total gas flow. We have to be careful with CO2 because you know what happens with CO2. It creates acid, and then pH is going down. So you have to control the flow of CO2 and pH in the culture, so you can balance that. Important is to remove O2. Of course, the oxygen will be produced there, and the excess of oxygen will lead to photooxidative damage, increase the rate of photorespiration, and that will suppress the overall productivity. So somehow O2 has to be removed. Temperature and pH, of course, temperature is very important. You have a different algae. Some of them grow on the very narrow range of temperature. Some of them can grow from 5 to 35 degrees. So depending on the organism which you want to grow, you have to control the temperature. It's 21st century. Controlling temperature is really not difficult. So there are many systems, off-the-shelf system, with which you can control the temperature. Before you start, I don't if you it depends if you have continuous or batch culture, but before you start with inoculation, before you start to put the system in operation, you have to sterilize it somehow. You can do that with ozone, but this is expensive, difficult to use. You need all kind of safety stuff, because if you inhale it, it will damage your lungs. So it's expensive and difficult. So they say that it's better to sanitize, and it's very easy to do that with the bleach, to do that with steam. And if you use bleach, you have to dechlorinate, or you have to, like Anna said, you have to bubble the air in for some period of time in order to chlorine to just evaporate into the air. So if we talk about some operational strategy, if we talk about protocols, you have to optimize basically and the balance, the parameter of light, CO2, O2, pH, and the temperature. And you have to define that very carefully, because that definition will basically affect your final production of algae. Harvesting methods. So you know that we can say that it's a dilute solution, and you have usually two common harvesting approaches. It's a flocculation and centrifugation. Even if you use flocculation to flocculate the cells, you still have to use centrifuge in order to remove the most of the water. Fermenters are a little bit different than photobioreactors. They basically are same in the shape, and like they say here, it's you can buy fermenters for 1 liter to more than 500,000 liters. The available, but they are pretty expensive. So there are some common relevant parameters you have to control. Of course, pH, temperature, harvesting, and main differences between fermenter and photobioreactors are energy source, what we said in the beginning, circulation, supply of oxygen, because fermenters need oxygen, and photobioreactors don't need oxygen, and then sterility. You need high degree of sterility in fermenters. So here you can so I don't read that. You have a photobioreactor and fermenter. Big difference is energy source. You use light in the photobioreactor and organic carbon in the fermenter. Cell density is higher in the fermenter, so productivity per unit of volume is higher in the fermenter than it is in photobioreactor. Limiting growth factor is light in photobioreactor. One of the limiting oxygen is in the fermenter. Harvestability, you have a denser population in the fermenter, and is a less difficult harvest. How the vessel looks like, you have to be very careful how design this, because you have to take into consideration the light penetration. That's why you said this, you usually use cylinders in the photobioreactors, or you use flat surface, thin perpendicular tanks, in order to be sure that the light penetrates effectively through the medium. Sterilized, most of photobioreactor can't be really completely sanitized, but you can completely sanitize, and you have to completely sanitize the fermenter. Availability, bioreactors are often made in-house. We said it's easy to make them if you know what you have to put into consideration. And fermenters are commercially available. They are not easy to custom build, and here you have to have some engineering skills in order to build the fermenter. Fermenters are centuries old, so it's not something what was invented yesterday, but the photobioreactor started when we start to grow algae, basically. So it's 200 years old technology. So for fermenters, we said that energy source is different. We need carbon as an energy source, so we need oxygen. So we need aerobic reaction in the fermenter. And we need, so the source of carbon is usually glucose, but people use different sources like acetate, citrate, alcohol, and other organics were used as an energy source in fermenters. In order to allow the proper gas exchange, you have to be very careful with mixing, and it has to be uniform nutrient distribution, and to basically adequate gas exchange in fermenters, what is basically done, but adequate mixing. So you can do this again with the airlift principles, or just with the air bubble column. Why we said that we have to sterilize fermenters? Very good, because we provide fermenters with the organic carbon, with a nice temperature for bacterial growth and the fungal growth. So it really has to be sterilized, and inoculum has to be really clean when you start to produce algae in fermenters. You can You can use steam, you can use UV, you can use even gamma rays or X-rays and different chemicals. Hydrogen peroxide is widely used, ethylene oxides, and I don't like for maldehyde, and they use for aldehyde too. You see, fermenters look much more sophisticated than photobioreactors. See, there is lots of control devices here. It's completely enclosed, and of course, much more expensive. So some of algae, you know, I just put different species that are growth in, let's say, larger scale in the fermenters. We said that 500 liters, 1,000 liters is the biggest fermenter. I never saw something like that, but and I don't know how much that costs. But these are the species that were successfully grown in the fermenters. Some strains of chlorella, you know that chlorella has a different strains, and I remember when we were producing chlorella for finfish hatchery and fish larvae, we were, of course, we were feeding brachiones and or artemia first, and then fish larvae. Some of chlorella were completely nutritional zero, and some strains of chlorella are very rich in especially fatty acids. So some strains grow very good under heterotrophic conditions, and they can double the population in just few hours. Now we'll go to the open production system. What is open production system? It's very difficult to say. When people talk about open production system, they usually talk about outdoor system, something what is outside. But you have open system, what I would call open system inside too. If you have tank and the surface tank is open to the air, you basically have open system. If you have the bags, plastic bags I showed to you, you can call that open system too. On the other side, you have, on the other hand, you have a closed system that are outside. You have we will see that you have a acrylic, you know, tubes. They are outside, but the system is closed because the media never gets into contact with the atmosphere. So what we're going to call closed and what we're going to call open is very difficult to say. But in literature, they always divide this open system is something what is indoor, and closed system is something what is outdoor, what is indoor. So outdoor system are ponds or tanks that are placed outside of some building, some construction. Most of the commercial size productions, if you produce algae, especially if you produce that for biofuel, if you produce that for some kind of pharmaceutical purposes, most of the mass production system are outdoor systems, so or open systems. So advantages and disadvantages, we said it's much cheaper than photobioreactors or fermenters, but it's limited to a number of algae species. Some algae will never grow very well in the outdoor system. They're just too sensitive. They're not very competitive with the other culture. So you have to be careful which species probably Gabriel can take a better hand, which species you're gonna select for the outdoor cultivation. And of course, outdoor systems are restricted to tropical and subtropical zones because you don't want to go really outdoor in the continental climate, or you can limit your production to 6 months, and then you just close the facility. So these are some species that are now grown in the outdoor open ponds. I don't want to talk too much about species because you have heard this before. So design, the two most important criteria is light penetration and hydrodynamic in the pond or in the open system. Usually pond areas range from 1 to 200 hectares. That's why I said that most of the mass production is done now in the open system, with average depth of 20 to 30 centimeters. If you have it up to 30 to 20 to 30 centimeters, you don't have to be very careful about mixing. So you usually move that slowly. You can use it. You will see different things to mix it. So if you have deep ponds or deep tanks, like say, I think it's mentioned here, the first production of algae for aquaculture was done outside, was done in the outdoor ponds, and they were rather deep. So they were mixed by aeration and used for a relatively small scale production needed for aquaculture. And then Japanese started with circular pond, where they were used, they were produced chlorella. They came up with very nice strain of chlorella, rich, nutritionally very rich, and not very sensitive for the outdoor cultivation. So then you have rectangular ponds. You saw that probably on the internet with a paddle wheel, and they're usually used for spirulina and Dunalia salina, and of course for Hematococcus. And this is the most efficient design for the large scale culture of microalgae, because it's not very deep. It moves the water constantly, and it mixes the water with paddle wheels. We'll see the picture of it. So these are different types of production systems. These are the tubes I mentioned. You see, it's a basically completely closed system, and you pump the water through this transparent system where you don't have to mix. You mix it. Basically, mixing is achieved with a water velocity. So each cell gets in the contact with light, and these tubes are not very wide. And it's a very common system now to produce algae for pharmaceutical purposes. These are some of the tanks that are placed outside. And I already showed this to you, but this thing can place indoor or outdoor, this flat-sided rectangular. And this is different kind of tanks that are outside tanks. So it's an outdoor tank, it's an open system. You can recognize this one. You can recognize tank like that. It's like the municipal wastewater treatment. And this is how basically this tank was adjusted somehow for algae, for the algae production. This is, you can see bubbles here. This is just rectangular outside tanks with lots of bubbles. They provide vertical movement of water and also CO2. So mixing, of course, we already said, prevents cells to settle and avoids thermal and oxygen stratification of the pond. So in the summer, of course, especially if you have not only the water, you have cells in the ponds, you will get the high temperature on the surface, and because the penetration even of the infrared light, it's difficult, and at the bottom you will have a lower temperature. So when you design pond like this, you have to put in consideration the interaction among the sunlight, water velocity, water depth, and design the pond around that. Raceway ponds. So raceway means the narrow, long ponds, where I said the mixing is with the water velocity, are generally mixed with the paddle wheels. earlier design, they're using airlifts, propellers, and drag boards. Drag board is like a, sorry, like the board like this you have in the pond, and you just drag this. It doesn't touch the surface, and drag this to the pond, and this is how you mix. And it's very efficient if we're talking about mixing, but it's very difficult. It's very difficult to manage. How you're gonna construct and design the ponds? So they can be constructed. They can be of concrete, or even just dig the raceways, and they use some kind of plastic liners. And so several liners are available, and you have to think about the cost. You have to think about the life of the product, because the UV lights will deteriorate the material, and what effect the material eventually have on the growth of larvae. Will you get some of this plastic in the water? Now it's very in to talk about plastic and what plastic does to the drinking water, what plastic does to the seawater, what plastic does to the fresh water. And now, at a higher temperature, above 20 degrees, you will get some chemicals from the plastic in the water. Alternative to the PVC is this chlorinated polyethylene, and it's safe for the human health, but I think one or two species of algae doesn't grow well in the chlorinated polyethylene, and these are these raceways. So this is something what is widely used now in the production of the open system production of the algae. You see the paddle wheels, they constantly rotate, and then they create the movement of the water through this raceway. Well, it is impossible, like we talked already, to prevent contamination in open ponds. The contaminants, are bacteria, viruses, fungi, other algae, zooplankton, but other contaminants that come from outside includes insects, leaves, and other airborne material. How you're going to control that? You have to operate that effectively. We were talking about some protocols. And like I said, the laboratory protocol is something ideal, something you will never create in the industrial system. Not only in the alga production, but any other production. The most difficult step is the step from the successful production of some aquatic organisms in the laboratory to the production to the large scale production. So all these protocols in the laboratory, you will try to somehow adapt to your mass production, and then slowly build your own protocol. Every facility has a different protocol, and you can't come up with a protocol right away. You try to use everything what people use in the lab, but little by little, you will adjust that to the condition you have in your own facility. And then you have to follow that, really follow that, because you work with a micro object. You don't see what you're working with. You don't see what is in the inoculant. You don't see what is in the water. So the only way to be sure that everything is okay is to follow the protocol, and never to avoid any step of the way, because you avoid one, you have no clue what is going to happen. One mistake will build up on the top of the other, and you will be completely lost. You will just have to throw everything to the sewer and start all over again. It's much better than try to fix the problem sometimes.
Depends if you have an hectare throw away 1 hectare of production.
Yeah.
It's really pretty hard.
Absolutely. I told you in aquaculture, I work on design of the aquaculture systems, And lots of companies just failed. Lots of investment money just went down the toilet because everything worked in the lab. And then you were producing something in the tanks like that, and then you enlarge tank, and it doesn't work like it worked in the lab. So it's something you have to be very careful about. Now, I don't want to get into somebody else's area, but I was just mentioned two cases how you can even work a little bit and try to kill and get rid of some of your contaminants or parasites, however you want to call it, even in the open system. Well, that's it. Thank you very much.
Any questions? Questions?
Oh,
You mentioned using ozone.
yes.
How do you even go about that? I have no idea. In general, do you pump it into the system and sort of use it?
You use the water that is saturated with ozone, and you pump the water through, or you can use steam, you can use something like that. So you super saturate water with ozone, and then quickly you just flash it with water.
What if you use air sterilization in the land, then you will definitely have some ozone creation.
Beg your pardon?
Do you use sterilization of air with UV lamp?
Yes.
Yeah, you use. So is there a generation of ozone?
No. No.
Not significant.
No. Actually, if you use ozone, in some cases, you use water with ozone and you want to sterilize the water and use this water to culture algae. Then this stream goes through the UV light, and UV light will just destabilize the ozone.
Yeah, depending on the
Yeah.
wavelength, right?
Yeah.
Is there some kind of material that is easy to clean and at the same time not toxic to algae?
What kind of system do you talk about?
Or raceway or bioreactor?
Some material that is easy to
Yeah,
clean.
or some, something you can put in there.
It's always difficult to clean this,
Exactly. This
So
is what I'm
when you're done
asking.
with the production, it's better to put the new line up. So I like something that is not expensive and you can use once, and that's it.
Yeah. So, PVC. No.
Because you never know what will happen if you use iodine, if you use not iodine. What? S čim steriliziramo mi?
Šta?
Nije jod, nego šta je?
Kloran, šta?
So chlorine, you never know what chemical reaction we're gonna get there.
Yeah.
If you use ozone, it will.
With my personal experience, I cannot. PVC is a nightmare because, well, it's expensive. One, two, it's if you scratch it, you ruin it.
Yeah.
Then it's sensible to the light. So after some cycle, you have to throw away the PVC because the light won't penetrate inside.
Yeah, no.
And this is really terrible for the bioreactor system. The best option I found is PAED. It's really cheap. It's clean. You can use chloride, and well, it's kind of robust liner that you can add, but it's just for open pond. You cannot build
Yeah.
bioreactor with PAED. And the most important things is not sensible to the light, because after a while, plastic solution in general are really sensible to the light. After some time, when it's exposed to the light, they grow.
Yeah.
Just grow.
And you never know when it's going to start.
Yeah, and it's really dangerous if it's growing while you are producing it, because you're losing all the calcium and the doctor.
Thank you, Yurica. Thank you very much.